Hey YouTube, it's Dimitri, and today we're going to talk about a paper that I recently published here. We have a subsequent paper from a colleague of mine who's working on more simulations, more analysis, but more or less this is the Kurtosis conjecture for decision trees. This should apply more broadly to other models, linear models, for example, as well, linear regression. But it's getting into the fact of how do you detect the amount of proper information being extracted from the data that you have, and more or less prevent overfitting or underfitting, and having some sort of tool or metric to diagnose this here. So one, this is a conjecture. So this is an opinion or a conclusion or summary that I have drawn based off of industry experience. By definition, a conjecture is more or less an opinion or conclusion or summary off of incomplete information. So this is more or less my presentation of what I see coming out of this. But let me dive on into the details here. I will post the paper below if you're interested. As my colleague's other paper gets posted, I will make another video on that as well. But let me just get into the basics here and kind of give you the intuition, right? This is not intended to cover every and all aspects of this, as this idea has been in my head since, I don't know, probably 2017, 2018, 2019. I've been working through this and it seems to hold with industry data here. But let me jump into quickly what is kurtosis, why this matters, and how we can actually use this and kind of interpret this from my viewpoint. So to start off with here, kurtosis is going to be the fourth moment, statistical moment here. If you're unfamiliar with moments, you have mean, which is the first moment, you have variance, which is the second moment, you have skewness, which is the third, and you have kurtosis, which is the fourth. Let me just draw a distribution here, and no, this is not the normal distribution. This is just a bell-shaped distribution of all. When you take an average of all these data points, which this is symmetrical, so the average is going to be the first moment. The second moment is going to be the variance. So variance is the second moment. Now, the third moment in this case is skewness. Skewness is essentially zero. But if you have a skewed distribution, right, the skewness is the third moment. And then the fourth moment is going to be kurtosis. This is what we care about. And I want to point something out because I think it is important to understand, as kurtosis is often challenging to grasp. The first and third moments are related. So again, the mean here, or the average, and the skewness, these two moments are related, the odd moments. We're going to look at kurtosis here. Kurtosis is related to variance, which is why sometimes it's hard to separate the two ideas. But I think pictures does the best. You have essentially the tailedness is what we like to call it. So the tailedness, I think that's how you spell it. Essentially what we're looking at is how much of the data as a percentage is in the tails versus the core of the distribution, or the center portion of this. So if you had something that looked similar to this, now, for example, the normal distribution here, if it is normal, or I should say standard normal, it might actually be required for standard normal. The kurtosis is equal to 3. Now, some people make an adjustment and they subtract 3 from everything so that kurtosis centers exactly at 0 for mesokurtic, which is a nice, well-behaved distribution here. So we call this one mesokurtic. It is technically one word here, but this is well-behaved. Then you have what's called platykurtic, which is kind of like a flat plate, right? Think about this as a plate. So this is going to be less than 3, and this is called platykurtic. And then finally you have leptokurtic. So leptokurtic is more or less the tails are pretty long, and it centers right in the middle, but the tails, we call the tailness is heavier. Now this seems counterintuitive when you look at this picture, but essentially there's a lot of data in the tail itself that goes very, very far out here. And so this crazy distribution is going to be called leptokurtic, and leptokurtic is going to be greater than 3 here. Now, when you think about this from a finance perspective, just trying to get the intuition here, skewness is bad. So we come over here, you have skewness, right? If this is going to be the center, let's say this is 0. Skewness is bad because it means you're not accurately predicting something, right? You tend to have a bias to either way over predict or way under predict. So this is not good. When you get into the fourth moment, which is the fourth moment we talked about here, which is kurtosis, the fourth moment itself is bad as well, because what it's saying, and again, it depends on the problem. So you got to think about this from a business standpoint here. But imagine when you're trading, right? If all of your trades are almost accurate here. So your skewness is near zero, but your kurtosis is quite high. What ends up happening is you're almost always right. But when you're wrong, and not almost always right, let's say 50%. Let's say 50% of the data sits here. 50%. The other 50%, when you're wrong, you are vastly, vastly wrong here. Like a position is so wrong, it's going to explode. So not getting off tangent here, if you're in the trading space, investing space here, this is why diversification and looking at investment position sizing is critical, because if this becomes an issue here and you have high kurtosis and you miss the mark and you have too much in that position, you'll blow something up. So again, it depends on the application, the problem here. But these are the 4 moments. This is what kurtosis is. And so now back to the paper here. What I am talking about is that the model residuals or the model errors, we're going to look at the kurtosis for this, okay? And this is what I'm talking about. So when I've looked at this from an industry stance, so I've looked at real industry data. I was in model validation in most of these firms. I've been in model development now as well, heading up quant risk and research, which includes model development, model validation, implementation, the whole gamut in the research piece here. Looking at this from different views, the models I consistently see being built, at least in the credit side of this, so looking at the banks here, I know they're overfit. And one of the easiest ways to prove this is that you can take these ridiculous model structures they develop, you can trim them way back. So you take like XGBoost, you reduce the complexity, the depth, the number of trees and all that. And what ends up happening is the model still performs almost the exact same on the actual development or the training metrics here, but it improves significantly in the testing. So the model's overfit. That's not an issue here. But when I model these out, I always look at the residuals, and it seemed like almost every time we would consistently see distributions with very, very, very high kurtosis. Kurtosis numbers in the 12 plus range, which is super, super large. I'd even seen trees and developments that were provided such that leaves would have less than 10 or 15 observations in there. Now you're thinking like, who cares? Well, these are millions and millions of observations. We might have 1 to 5 million records in a data set. And if you have a tree so large, or a decision tree based model, it could be random forest, XGBoost, it's definitely overfit. Like it's so far overfit, we know that it's way overfit. But we would consistently see this in the kurtosis. And then when I'd go in for model validation and I would scale them back and reduce the complexity and we'd remain fairly accurate, the distributions would come down. Now, they were never close to 3, which is the conjecture I have, but you might end up with maybe a 7 to 8 on kurtosis, which is still very high. But this clearly was an improvement because accuracy didn't really change or affected. We tend to get better, more robust models on this. And when we would do additional out-of-time testing here, the models seemed to stand better. They were more predictive. They're more generalizable here. So this conclusion has come from my industry experience at multiple firms. This tends to be what I see in practice here. Now, again, financial data as a caveat here, financial data is unique because it changes with time. People are not predictive. We're not estimating one solid relationship. So to put that in perspective, we're not estimating gravity. We're not estimating pi. It's not one thing. And machine learning is very brittle and rigid because there's this overfitting of a pattern. We're not actually looking at often the relationships because often the development teams aren't thinking about this more theoretically. They're spending more time trying to build models fast, which I get. So let me get you into the intuition here. When you have a decision tree, we tend to view them right like this, and you have some sort of split. I'm going to try to steer you this other direction. Instead of looking at it like a tree, let's look at it like a space. So in this case of a decision tree, if we said, okay, variable 1 is less than 10, it goes left. If it's greater than 10, it goes right. Essentially, this is going to be 10. If we split the space in half, this is going to be the left side, which is this leaf here. This is going to be the right side, which is this leaf here. And if you had a bunch of data points in here, some are like this, you would use whatever function possible to do the calculation at the end of the leaf. Often it's just the average. So you take the average of these data points here, take the average of these data points here, and you would say, I don't know, maybe this is 2 and maybe this is 2.5, and you would end up with a decision tree. Now, I want you guys to think about it in this square space, not in the decision tree, because I think it makes it a little bit easier to understand. So visualizing decision trees in this space can get challenging because this is univariate, looking at one variable. We're only looking at it univariately now because it is simpler and easier to understand. If you were, instead of doing a decision tree box like this and splitting this one variable into partitions, you could think about univariate as doing some sort of cube and then slicing out, pieces of this cube into different sections and chunks. And as you get, the number variables increases, it's hard to understand and grasp this from a visual stance here, but let's just bear with me from the univariate and then mentally think about how you would apply this to a multivariate case. So when we have some sort of space here and we have a bunch of data points, right? I don't know what they look like here. We're going to have a bunch of data points, and let's just say for the sake of this, right, it's nonlinear, which is maybe one of the reasons we are using the decision tree here. If we go to look at the complexity of the model here, we're going to have two things we're going to need to consider. One is going to be model structure. That's going to be the size, the type. So this is, type of model. This is going to be size of model. I think it's going to be it for the decision trees kind of. But I mean, you could think like, are you doing a simple cart model? Maybe you're doing XGBoost. Maybe you're doing AdaBoost. I don't know, random forest, something like that. And then you're going to looking at size as well. So how big is the tree? How many splits they are? How much pruning did you do? Again, with the size of this, you could also have complexity. Maybe it's how you trim it. Maybe it's a lopsided tree, and there's reasons to do that for fitting purposes. The second piece is going to be variables. Now, the number of variables in the model also is a piece of complexity, but it's not model structure, really. It's not how the tree is built, or if it's boosting, you're setting up multiple trees, or you're doing random forest where you're averaging across multiple models, essentially, which is another structure. The number of variables of themselves increases the complexity of the design of the tree here. So these are things to consider. Now, when you think about this, let's just say we do a quick split on this. So we run this through, we look at all the different possible splits, we come up with some sort of split here, and let's say it splits right here, and we take an average here, and we take an average here, and it generates some sort of model error here. Now, the model error is going to be the difference between the data points and the prediction here, right? So in a decision tree, if you had a prediction of, let's say, 5, and this is, I don't know, say 3, the error is going to be these offsets, or the differences between all the data points. So what we're saying with this is that when we would plot out the residuals, it would most likely center somewhere around 0. You would hope. There might be some skewness to it as well, but we look at the kurtosis on this, and it would definitely be platy. So it'd be platy-kurtic because the residuals from this, again, overly simplified or the underfit model would be very flat. It would be displayed across the board, right? We have some of these right here, which are very, very close to 0. So those would be right here. And then you would have like these green ones I showed before, which are very, very far away, right? Even like these ones are huge. And that would be, like these ones are going to be over and these ones are going to be under. So you would have a large pockets in here, but more or less the model's underfit. And so we end up seeing a platy-kurtic distribution within the residuals here. Okay, so now if we rewind here a second and we look at this again and we say, let's start increasing the splits here. So let's focus on, again, we're not going to focus on the variables. We're just going to use univariate for simplicity for explaining and understanding. We're going to focus here on the model structure. Let's keep splitting this simple cart model, right? This simple decision tree out. You can see here, based on the splits, what we would end up probably seeing is we'd have a split here, right? Because there's this pocket here, which we would get good accuracy with. And then the model and the algorithm would look at this and probably start splitting. I mean, this seems to be a pocket here, so it would probably split somewhere around here, and it would split somewhere around here. And I don't know, you might end up splitting out here because you'd average here and have a good model fit here. And let's say, just for sake of this is going to be fairly optimal here. What we would end up seeing with this distribution, again, is we had a very platy-kurtic, but now when we have these sorts of estimates, right, you have these sorts of averages that are pulled and calculated here, the gap or the model errors are getting closer and closer and closer to 0. Now, that being said, we still have these outlier cases. And I'm going to be very, very careful in how I say this because I see people say, Dimitri, your method is not robust to outliers. I don't want it to be robust to outliers in a general sense because I feel like people say that hand wavily. They don't mathematically or statistically derive that. In most cases, outliers aren't an issue of an error of a user input. It's an actual use case, especially in the financial space here. There are data issues, there are data entry issues. I know I deal with this a lot. But at the same time, when you have a lot of outliers as well, these are things that the model is not capturing. So what ends up happening is we added all these extra fits. Again, this distribution is going to start changing. And I would argue it starts to look more like this. And as we add more and more splits, it starts to look like this. Now, the question being is how far do you go, right? Because as I continue to split, if you're familiar with how decision trees work, you could literally oversplit this such that every data point was split so granularly. So, you just keep splitting and splitting and splitting and splitting and splitting. Every single data point has its own leaf. So when you have a dot like here, the prediction is the actual value itself. And what ends up happening with this distribution is it looks like this. It's a line. There is no variance from that. We have 100% overfit guaranteed. The model error is 0 on our training data here. So now you think about this going backwards. If we removed a lot of these data points, a lot of this overfitting, we would slowly go back and towards, again, so this is going to be, I'm going to say 100% overfit, just mentally. Kurtosis is leptokurtic, and it is leptokurtic to a disgusting amount. It is way too far. We went way too far. So on this first original curve here that we talked about, we are way, way, way underfit. This is the simplest process on the left-hand side. When we overfit 100% for kurtosis, you're all the way to the right side. Your model error is 0, and it is definitely overfit because, so to give you guys perspective on this, in finance, when you go to use this model in a week or a month or a year, what ends up happening is this data set might have a similar shape, might have a similar relationship, which we're trying to model here, but these data points have now shifted. And so, you still have this, but maybe the original shape of this model itself looked something like this if you just drew the line out. And if you fit a line to the new data points, it shifted like this. And so what ends up happening is because you 100% overfit, your model errors explode. The model fails instantaneously. It is way too brittle here. And so for finance, one of the hard things to think about is how much time will that model last, and is that amount of time reasonable, right? It takes us so much time to redevelop models. In the loan space specifically, where I'm working and where a lot of this is derived from, when you end up making a decision, I'm stuck with that decision for an extended period of time. I make a loan for 5 to 7 years in the auto space. In the mortgage space I've been in, it could be 10 to 30 years, right? So you're thinking about, you make the decision today based on this shape. If the shape of it changes tomorrow, often the residuals, the kurtosis explodes, and it will go from very, very, very leptokurtic, and often within a short period of time, 3 to 6 months, it will start to deteriorate depending on the problem, but you will all of a sudden go back into a platykurtic distribution, meaning the model's not holding. The accuracy you thought you had isn't holding. One way to do this is, again, the testing, right? The testing data set, which we already know and already use. I call this out of time in finance because I require it to be split based on time. You have an out of time sample. You cannot sample across the same time space. And when you end up doing this, you end up getting a model that is more robust by looking at these. Now, back to the kurtosis of this, though, if we end up not oversplitting, what I tend to find is that a well-fitting model kurtosis should be close to mesokurtic. So it ends up having this balance here we see from underfitting to overfitting. For some odd reason, and I've racked my brain on this, we end up near mesokurtic. Mesokurtic does not mean normally distributed. I want to hit that home very hard. Just because the normal distribution is mesokurtic does not mean all distributions that are going to be mesokurtic have to be the normal distribution. You can have different types of distributions that are mesokurtic here. So Please bear with me on that. There's nothing here saying that needs to be normally distributed. All I am saying is mesocurtic or near mesocurtic tends to be the correct metric here. So when you fit a model, I'm going to say from the conjecture, we should target somewhere around 3. Now, that doesn't mean how we use the metric here. So how do we actually use this metric here? Because I'm not saying you fudge the model until you hit 3. You hit mesocurtic, right? That's not the goal here. The goal is going to be a few different use cases. One is going to be model comparison. So model comparison would just be saying, okay, I have built 2 different models. I don't know the complexity of the models. I'm going to assume everything I have given to me is what I have. There's nothing else I can do. We're going to have a model with a kurtosis and the residuals of, I don't know, say 12 in our example. And then we have, this is model 1, model 2, model 3, and model 4. And let's say we have, I don't know, 4.5, 7, and I don't know, 8. What this would help you do is look at these different models, and these models could be all very different on this. Again, same exact development data here, same exact out of time data, so you can compare these. Let's just say this is going to be testing for the sake of it. You could have out of time metrics for this as well. So this is development. What I am saying from a fitting perspective here is this isn't telling you this is the right model. It has the right variables. It has the right, structure. It's optimal. But what I am saying, when you look at these different sorts of models, you take business insight, intuition into this, conceptual soundness into the modeling framework, and you believe these 4 models are well done models, you can come in and say 4.5 will probably be the most robust model. And again, you'd want to then look at your out of time testing as well and see what the numbers are. Maybe it's 8, maybe it's, I don't know, 7.2, maybe it's 6, maybe it's 10. You can look at this and say, okay, the kurtosis is 4.5 here, it's 7.2 here. Is that good? That seems like it's deteriorating faster. This one is going to be 7, right? This is the kurtosis is 7. This one is 6. This one seems to be getting better. Again, being a real quant, you ask why. Why is it getting better? What is different about the structure? But the kurtosis piece here will help you understand what is going on with that. So that is model comparison. Now, the second one is going to be information. And I'm just going to call it information theory for a lack of better terminology here. Information theory is saying, I already know the world isn't perfect. I know I don't have all the right information. I already know that I can't build the correct, I'm going to put correct here in air quotes, the correct universal theory, the idea here, right? So I'm given, let's just say there's some sort of space here. I have variable 1, variable 2, variable 3, and variable 4, just for simplicity. Often in practice, variable 1 and variable 3 I have. Variable 4 and variable 5, right? So these ones here, there's no way to measure them. I don't know they exist. I don't know how to get them. This is the unknown space here. So this is unknown. And in practice, we know that there's always a missing variable bias somewhere. We don't know how to capture it. We don't know how to get it. But in the financial space, I have to make some sort of decision and I have to make it quickly. So given I have variable 1 and variable 2, which variables do I use? Do I use just variable 1? Do I use just variable 3? And more specifically, maybe there's variable 5 out here. But this is separate. It's not actually part of this. So you have variable 5 to consider here. What the kurtosis helps to explain as well from a theory standpoint is how much of the proper information am I extracting versus how much noise am I extracting here. So if I said variable 1 and variable 3 are truly drivers, they're true relationships, variable 5 is not connected. It is not supposed to be in the model. It truly does not drive this. As you know, when you fit models, variable 5 might be good in correlation. It might be good in fit. And so when you end up building out some sort of model structure here, right, the question being is, if variable 5 comes in here, how is the right information being extracted and not extracted? So I would argue from this conjecture, what ends up happening is we add in this variable 5, which does not matter. This will actually increase the kurtosis above where it should be. And so when we go back to this comparison stance, hopefully you can look at these models and say, hey, this model, kurtosis variable 5 is in this model. It is not in the other models. Why is that? So when you have the kurtosis and it is near mesocurtic or closer-ish to mesocurtic, right? It's a fuzzy thing. I don't think we will ever hit perfection because we never have all of the true relationships to get to that sort of variable here and that sort of structure. And as that case, as I mentioned, you'd probably end up with just a 0 because it is absolutely perfect. But I would actually argue in financial spaces and other real theory, you'd end up with actually probably a meso-Kurtic distribution simply from data entry or data measurement errors. So this is how I think this conjecture works. Again, my colleague is working on another paper, doing simulations, testing, writing out the true relationship as we kind of talked about here, because we're artificially generating it, so we know the actual true values, and then removing pieces of it, creating that sort of bias where we just don't have all the information in it, and then doing simulations and testing and looking at this. Her findings are a little bit different than what I have presented here. This is, again, just my brainchild of what I think the conjecture is, how it works, why it works theoretically. But again, more testing, more challenge needs to be done. So I'd love to see people produce other papers and say, Dimitri, you're wrong 100%. Or in the case of my colleague, you're partially right, but this is more or less how it outplays into real world scenarios here. So again, the model's not to be designed and said, hey, we need to hit meso-Kurtic, if not, your model sucks. It's really a comparison tool. It's an information theory tool as well, looking at how much of the true information can we extract, and then realizing the rest of the residuals are things we just truly can't model, and we should not continue to increase the model structure or add other variables because they truly do not matter to the model fitting process here and building a correct, robust model. And I want to emphasize that a lot here. Robustness, a model that stands on its own 2 feet, that has stability across time, that has great accuracy, and is not impacted by the data structure or the sampling methodology too much, right? Some more robustness to this. I believe this structure itself will help you to build more robust models that will last over time, that will have better estimations or more robust estimates of the model structure and the actual model coefficients or the design of the model itself. So anyways, that's my conjecture. Again, I will put a link to my paper in the description below if you're interested. Thanks for listening. Thanks for watching. And as always, until next time.